In the last lecture, I mentioned that it is possible to solve a problem of dynamics by converting it into a problem of static equilibrium. Today, we will first explain the basic principle behind this technique, and later I will illustrate the technique with the help of an example. Here we have told or stated at the beginning that all the external forces and moments are keeping the system in static equilibrium, but when you consider the motion of a mechanism, it is not in static equilibrium. So, how can we use this wonderful principle that each and every link is in static equilibrium, and you can analyze each and every link separately for equilibrium when the system is in equilibrium, but if the system is in motion, how to utilize this concept or this principle? Let us consider that next. So, now let us come back to our problem, that how we make use of this principle that a system in static equilibrium means that each and every member is in static equilibrium. How we solve a dynamics problem using that. So, we will go back to our basic dynamics course, and I will remind you of a very widely used principle first developed by Alembert, and which is famous as Alembert's principle. What is this principle? Just a small or brief recapitulation of that. If we have a rigid body or a body, Alembert's principle says that under the action of externally applied forces and moments, whatever it may be there, and if you also subject this to some hypothetical forces, which I will explain very soon, which you call as inertia force and some inertia moment, then under the action, combined action of externally applied forces and externally applied couple, if we also add certain hypothetical forces which we call inertia force F I, inertia moment M I, then this body will remain in static equilibrium. Now, to understand this, that what are these hypothetical forces, inertia force, inertia moment, let us find out that. See, if we take simple case of a particle, now if this particle has an acceleration a in this direction, so it implies that it must be acted upon by a force F, which is given by mass into acceleration. Now, it is almost trivial to you if I say that if this particle of mass m is acted upon by this force F, another force F minus F this system is in equilibrium. It is almost a trivial statement. So, what is meant here is that rather now therefore, you can see that this minus F I is nothing but what I was telling minus M A. So, if I tell that the particle is acted upon by a force F and another force minus M A, this system will be in static equilibrium or particle will be in static equilibrium. So, this is what is D'Alembert's principle, though it is not just as trivial as it sounds, but it says that to a body, if we subject the body to the actual external force along with a hypothetical force which is nothing but minus m into a, which we call inertia force, the body will be in static equilibrium. Now, this is for a particle. Let us just extend this to a rigid body or extended rigid body. So, we draw our old friend, the rigid body, whose center of mass is c, its total mass is m, and its moment of inertia about an axis passing through the center of mass is I c. Now, if the resultant effect of all the externally applied forces and moments is represented by a force F, I have already shown that this will produce an acceleration of the center of mass which is a, given by F by m, and it will also produce an angular acceleration alpha which is given by F into E by I c, where E is the perpendicular distance of the force or eccentricity of the force. Now, let us imagine what is that force. What is that force which is equal to minus m a acting here and a moment minus F e by I c acting about an axis passing through the center of mass. So, we know it is nothing but therefore, the negative of the applied force. So, this is nothing but the resultant of an inertia force minus m a and a moment, inertia moment, which is minus alpha I c. So, now when this hypothetical force is applied along with the externally applied force F, what is the resultant effect? They cancel each other, or this F, or which you can call also as F I, inertia force, cancels the externally applied resultant force, bringing the body in static equilibrium. So, we can now call, or we can now say that if a body is under the action of a number of forces, and the acceleration of the center of mass is a and angular acceleration is alpha, then if I apply a force which is minus m a and a moment which is minus I c alpha, then under the combined action of these inertia forces and inertia moment, and the externally applied forces F 1, F 2 and F 3 which produce this motion, this system will be in static equilibrium, because the resultant effect of these force and this moment is nothing but producing a force which is equal and opposite to the resultant force produced by these. That means, they will nullify each other and the system will be in static equilibrium. So, this is the technique which we will use, this D'Alembert's principle, and we will add the inertia force of each and every member to it, and then treat the whole system as in static equilibrium. Just like that, suppose we go back to our original example, which I am referring back again and again. and let us consider a more realistic and more complicated problem of finding the loading on the connecting rod. How do you find out? Mass of this is given as m2, mass of this is given as m3, center of mass this is c3, moment of inertia about this, about an axis passing through the center of mass for the third body or coupler is IC, and of course, I will not need that now. This can be also given some mass and some moment of inertia about this. But the motion is given, that means I know the velocity of this. So, this is having an acceleration a. Now, if this and this point is having an acceleration in this direction, centripetal acceleration, this has an angular velocity maybe in this direction, and it may also have some angular acceleration in this direction alpha 3, and this center of mass has some acceleration like this. So, we know now the complete motion of the connecting rod. So, if we separate it out, and now what will be the inertia force and moment on this? We know that inertia force will act here, which is nothing but mass of this link 3 into acceleration of the center of mass 3, a moment will be, it will be minus, moment will be what, I c 3 to alpha 3 minus. So, now if we add these forces hypothetically, then the under the action of these inertia forces and moment and the externally applied forces, which may be and maybe weight, gravity, under the action of these three externally applied forces to this member and applied inertia force and moment, this system will be in static equilibrium. That means, the total force will be 0, total moment about any point will be also 0. So, once we can come to this situation, the whole problem gets converted into a problem of static equilibrium, and there are various ways of solving this kind of a problem, and we will illustrate that by solving one particular problem, say maybe this kind of problem or a folding mechanism and so on. So, we explain the whole procedure of finding the forces on various members and joints and contacts by a definite example using the method explained so far. We will take the simple case of this slide rectangle mechanism, but the method is very general. We can apply it to any kind of mechanism with any number of links. So, first I will state the problem, and completeness of stating the problem is very important in solving this problem at this analysis. So, the data which you have to give is all the dimensions, that means this radius of this, length of this say point is A, this point is say B, this point is the fixed hinge or the crankshaft axis O. This angle at this instant we may consider to be theta, and we mention that this is rotating with a constant angular velocity, and a torque is acting on this, say moment on link 3. Say we call this link as link 2, this as link 3 and this as link 4. So, we should correct this to link M4. Our objective is to find out the total force on this connecting rod. Why I am taking up this particular member? Because you will notice that this member link 2 or the slider 2 executes a simple rectilinear translation, it is a simple form of motion. This crank, it executes a pure rotation with this as the center, also a simple motion, but this has both rotation and translation combined. That is why I am explaining the procedure for finding out the loading on this connecting rod. The first step what we have to do in solving this problem is determine the acceleration, I mean to say the linear acceleration of the center of mass, which we call AC3, and the angular acceleration of this link, which we call alpha 3. Now, that is a problem of kinematics, which we have solved enough number of problems, and we can solve these quantities like this once the velocity of this is given. Next, what we do? We consider only the link which we have to analyze. And we calculate the inertia force, which is Fi, which is nothing but minus m3 into AC3. We also subject this to inertia torque, which is nothing but minus IC3 alpha 3, which is the inertia torque for link 3 say. Now, we know that this and these ends will be subjected to link forces. You can also give some idea that okay, there is some external force acting on this, maybe the weight of this, but I think to keep the problem less complicated, we do not add any external force, which could be easily done. But we know that there is some force acting here, which is a reaction force here from link 4 to link 3, and a reaction force from here, which is from link 2 to link 3. We do not know these forces, but this reaction force, this inertia force and this inertia moment, that will keep the system in static equilibrium. That means, for this system total force will be 0 and total moment will be 0. That is the condition. Now, since the magnitude and direction of this force both are unknown, the problem cannot be solved directly like this. So, we have to say, for example, if we take moment about this point A, then moment of this is known, moment of this is known, but moment of this, which has to exactly cancel the total effect, is known, total known, but its direction and magnitude, two quantities being unknown, it cannot be solved. So, how we solve is this, that let us find out the component of R for 3, which is normal to 3, that we can find out. How? Taking moment about point A, we can write that if this is the perpendicular distance of the inertia force, that Fi3 into E3 minus Mi3 minus R43 normal to 3 into length of this member L. We could consider this as L3, since we are giving. So, we could consider this to be length 3. This total moment about point A must be 0, because moment of R23 about this point is 0, So, the moment of all other forces and moment ultimately must be 0. So, from this we can find out how much is R 4 3 N 3. Please keep that in mind. Next, let us consider link 4. Link 4 is also in static equilibrium under the influence of the external forces, torques and the inertia force. Now, this is rotating at a constant angular velocity, and if we do not put the gravitational forces etc., then we know that the moment which was acting on this from outside, the moment was being acted upon this M 4 and some force here R 1 4, and the force from this will be now exactly equal and opposite to, which is equal and opposite to R 4 3, whose one component we have found out. So, under the action of, since there is no angular acceleration and no and the center of mass will have some force, inertia force, which will be in this direction, because it will be pure centripetal acceleration. So, inertia force on link 4 will be purely radial force. So, if we take the moment about point O, the total moment must be 0. So, we can say moment of this is 0, this produces a moment M 4 in the clockwise direction, this produces 0 moment, and this produces how much moment? That we can find out by taking the normal component. This is R 3 4 normal to 4, and this length dimension is say L 4, which is nothing but R. So, we get an equation which tells that M 4 minus R 3 4 normal to 4 into L 4 equal to 0, or we find out R 3 4 normal to 4 is known. So, we have found out the normal to 4th link, a component of the spin force. Now, let us consider this point B. We have seen that this is R 3 4 and this is obviously equal and opposite, which is R 4 3. Now, we found out a component of this which we call R 4 3 normal to 3. If you remember, the link 3 direction was like this. We have also found out another component of this R 3 4, which is R 3 4 normal to 4, because link 4 or the crank was in this direction. So, this is 90 degrees and this is 90 degree. Now, you all know that R 3 4 normal to 4 is nothing but minus R 4 3 normal to 4, because R 3 4 is just equal and opposite to R 4 3 according to Newton's third law. So, we can say that R 4 3 normal to 4 will be just equal and opposite to this. So, now we find the situation that this is the component of the force R 4 3 in a direction which is perpendicular to link 3. This is the component of the same force R 4 3 in another direction which is perpendicular to link 4. So, if we know the components of a vector in two different directions, this is R 4 3 normal to 4 and this is R 3 4 sorry all 4 3 normal to 4. So, the vector will be nothing but if you draw perpendicular from the tips where they intersect, this must be the vector R 4 3. So, by considering the equilibrium of link 3 and equilibrium of link 4 and since they are interconnected at this location B, we have been able to find out the magnitude and direction of the pin force or the joint force at B. Once that is done, then when you go back to our original problem of finding out the resultant force on this, we have been now able to find out the resultant link force. We also know there is no other external force or anything, but it is under the action of the inertia force F I 3 and an inertia moment M I 3, and there is a force here we have to find out. This point was B, this point is A. Now, our job is to find out the last force which is still unknown on this. Now, this can be easily found out because we know that the system must be completely force free. So, therefore, under the action of this force and this force, its total force should be 0, or we can say that if we add the 3 forces, they will form a closed triangle. This you know for vector mechanics this, and if I for your benefit I slightly change the direction, making it this, not to make them align. So, you will find this is the inertia force, then the force here has to be such that it closes this triangle, that will be R 2 3, the force acting on this link from link 2. So, drawing the force diagram which has 3 forces here, the triangle can be completed and the last unknown force on link 3 at the joint A can be found out by this. So, therefore, now the whole link is under static equilibrium due to the influence of the externally applied forces at the 2 joints and the inertia loading. Of course, the problem is very general. If there had been external forces and moments acting on the link, they could be also taken care of without any difficulty, only it would have led to slight more complexity of the problem. So, this is the procedure that how graphically we can solve the dynamic force analysis of a mechanism. Now, this once that is known, we can go back to link 4, we can go to link 2 and find out the total force on those 2 links. It is quite possible, and once this force or loading is known, it will be possible for us to find out the bending moment, etc., compressive force or tensile force on any section of any member, and if the material is known, the allowed stresses are given, it will be possible for us to determine the required cross sections, not to allow any failure because of this loading. So, this is just the beginning of the force analysis when a system is under motion due to some external forces and moments. In the next lecture, we will start from this point with some more discussion on this and how to proceed further in the direction of design, and maybe 1 or 2 more examples to illustrate the procedure much better.